Digitize a math curve? What do you mean digitize a math curve? I got a bunch of points. All I got to do is just key them in, right? Yeah, but the catch is, how do you change this curve? All it is a bunch of points, and let's suppose you find out you're lean down around 2 volts and rich up around 3 volts. How would you go about adjusting that? By digitize, I mean convert this list of points that you've got into a mathematical formula. So now you can change the formula rather than guess at a couple points along the dotted line that you've downloaded here. Let's look at this little curve that I've downloaded here. This one's a 4-inch stock MAF from a Ford. You'll note that on the bottom especially there are clumps and gaps. And that could create you some problems if those clumps and gaps happen to be where you're having problems. Okay, so why would I want to take a MAF curve and convert it into a mathematical formula? Reason number one is any change you make to the MAF curve now becomes a change to the entire curve, not just a couple points somewhere on the curve. Digitization also creates the ability to make changes exactly where you need them. This makes for easy adjustments in that one area without totally upsetting the rest of the curve. Digitization also creates a nice smooth curve, no bumps or bulges that are going to cause you problems later on down the road. All data for making changes comes from your data logs. No guessing. If you have a problem area, say like a turbocharger or nitrous cutting in, this allows you to oversample that area if you want to. This technique also gives you a very maximum resolution, all the way to 30 points if you want it. You don't have to worry about selecting points with a 4-digit number from your data log. You can select points on an even number, making it much easier to search through your data log for points to work with. And yes, I found out this technique makes my life a lot easier when I'm tuning the car. All you have to do is look for the points on the data log and make those changes. Any change you make affects the entire curve. And of course, you get it right down low, it's going to be right up top because you changed the entire curve. Okay, here's the mathematics portion of the video. Relax, it's going to be brief. King's law's relationship between the voltage required to hold a wire at a given temperature for a given airflow rate across that same wire. And yes, guys and gals, that's exactly what a math sensor does. Okay, what we're really interested in, of course, is mass airflow. In this case, I'm going to solve for velocity, and then mass based on temperature is compensated for elsewhere in the program. So I'm going to just solve and let velocity be my guiding parameter here. Now I'm going to take that nice mathematical formula and transfer it into an Excel spreadsheet, and then I can work on my MAF curve in Excel. Now it's time for a reality check portion of this little program. Your chances that MAF curve you downloaded working perfectly out of the box, forget about it. Ain't happening. Anything you do to your car makes it breathe different is going to affect the MAF curve. In theory, of course, even going from a dirty air cleaner to a clean air cleaner is going to make your MAF curve different. Pretty small, but it's definitely going to change the curve. The stock MAF curve on my Mustang was a joke. It was really, really lean on the top end. Now, trust me on this. If you get this MAF curve right, the rest of your job tuning the car is going to be very, very easy compared to what you would go through if the MAF curve was off a little bit. Okay, to make my life easier, I'm just going to refer to a KAMRF as a cam. In this case, of course, cams below 1 are rich, cams above 1 are lean. If you think that disconnecting the emission systems is going to make the car run better, think again. It may make the car run worse if you don't compensate for it both in the program and in your tuning. Okay, all I'm going to say about this page is remember that it's here and refer back to it before you start making any changes to your curve. Here is how I've chosen to scale my voltages column. This is adjustable. You can change this to anything you want. If you want to oversample one area, no problem. You can do it right here. Okay, let's look at where I'm getting my points. In this case, this is a partial data log. You see the VMAF is sitting at about 2.01. Air charge temperature is 90. Engine coolant temperature is 144, which is really low. Should wait till it gets a little warmer than this. Lambs is around 9.5, and I'm using number 2, so the cam on that one is 1. So really here, This is just barely inside operating in closed loop conditions and barely acceptable to accept a point on, but I chose to take a chance on this one for demonstration purposes. Okay, if I look at the Lamsey and the cam, if I go back and take 1 instead of 2, basically what I'm looking at is around a 3.5% difference. Now, it's operating with the computer saying it wants to go rich, and the return value saying it's stoichiometric. So in this case, looks like 3.5 is the difference for round numbers, and I generally take about half of that and go with about 1.5 or 2. In this case, I'm going to go ahead and with 2 and use that as my calculation value here. Note that the white line is my selection line and the yellow line indicates the car is going into open loop. Here's my 45 mile per hour cruise point. Voltage here is 1.58. I've turned everything off but the MAF and the CAM 2 and Lamsey 2. I've overlaid them and now I'm looking for some average values. In this case, the numbers are coming back about 2.5% rich as commanded, and it's returning about 2% lean. So again, I'm taking about the half, around 2%. So I'm going to actually try to richen things up here about 2%. Here's the 55 mile per hour cruise, and this one's about like a split decision of a boxing match. If you choose Lamsey's 1 and Cam 1, it says it's stoichiometric. If you choose number 2, it says it's around 5% out. So in this case, I'm still taking a hold of 2, so I'm going to declare it again 2%, and basically I'm going to make a 2% change across the board to richen up the MAF curve. Okay, now I've got my 3 points. In this case, I'm not going to use set 1, I'm going to use set 2. I'm going to set up my target values in this location, and these will be the values I'm going to compare against what shows up in this location. Note that it'll be the second line down, the first is set 1. I made one change in the actual constants, and note the difference between this line and the top line. They're basically pretty darn close. Note that to make this change, the only thing I had to do is change the one constant in the B column for set 2. One little change updated the entire set 2 column, and it also updated the comparison between the running and the set 2 column, which gives me a percent difference across the entire curve. And now, without further ado, here's my latest MAF Designer spreadsheet. I will be posting this so you can get a copy of it so you don't have to create it. The main difference between this one and the previous one is it allows 5 different MAF curves to be used along with the base curve. You can use any or all of those curves to compare against one or the other, and your set points that you would choose to adjust the curves are totally independent for each set. On my previous spreadsheet, all of the set points were lumped together, so all 6 MAF curves had to use the same set points. Okay, let's dive in and take a closer look. I'm going to start with the set 1 block and just look at all the main parameters for that one particular set. Okay, let's start at the top, in this case voltage set points. Again, in this case, of course, they're totally independent. You can set these anywhere you want to along the curve. In this case, I've got them set up so I can take the MAF curve that I downloaded and convert it into a mathematical formula, in other words, digitize it. Kilograms per hour current value are the actual calculation points for each of my 3 selected set points. These are where you'll see the data change as you modify the setting constants for the particular MAF curve you're working on. Kilograms per hour previous target are the values from your previous MAF curve that were calculated corresponding to the points on this new MAF curve you're working on. Kilograms per hour set point adjust are the percentage adjustments derived from your data logs where you're trying to make the change from the previous MAF curve that you were looking at. Kilograms per hour target value are the numbers you're trying to match with your kilograms per hour current value. In other words, these are your target values you're trying to achieve. Now, as to how this works, I take the target values from my previous math curve calculation results, then multiply them from the set point adjust percentage. Again, these are derived directly from the data logs for the previous math curve for correction purposes. And the result of this calculation for each 3 points shows up in my kilograms per hour target values. This row is just my mental reminder as to how the adjustments are going to be made as far as changing constants and which direction the curve will start moving as I change constants. In this case, changing constant A in a minus direction or more negative will make the math curve greater, i.e. increase the math curve number. The initial values line in this case is blank because the curve that I'm creating is based on a downloaded curve. There were no initial values. There are 3 constants in the calculation you'll be changing. Again, these are pretty much trial and error, but it does go a lot faster with experience. In this case, of course, A, B, and D, since D is a revised constant off of King's Law. These 3 numbers are the only place you're actually changing the data. When you change the data in these 3 columns, you'll affect the entire math curve as a whole entity. And you'll see all the numbers up above in the current value change. For purposes of this initial math curve digitization, here is where the 5 volt or the high parameter current value and target value numbers came from. Note that the 2 volt and 1.5 volt are also in their respective rows down below. Now it's time to look at set 2. In this case, I chose my points at 1.6 volt, 1.8 volt, and 2 volts. I definitely do not recommend picking your points this close together. This is for demonstration purposes only. You really want to space these out and get at least upwards around 2.5 or 3 volts if you could with 1 point, and down as low as about 1.2 volts for the lower point. That'll give you a much more accurate curve than what I'm doing here. But again, this is for demonstration purposes only. Now, here are my previously calculated target values from my previous math curve digitization calculation. And again, these are from each one of the respective points, 1.6, 1.8, and 2. Now, after reviewing my data logs, I've decided I want to change the 1.6 volt value up by 1.8%, the 1.8 value up by 2%, and the final 2 volt value up by 2.5%. And here we see in my target values the results of those calculations. Now I go into my running row and start making changes in that row to try to get the current value numbers to match the target numbers. And here we see where all those numbers are in the spreadsheet down below after I finish my calculations. Now let's look and see how close my original digitization of the original downloaded math curve is. And as you can see from this column, it was pretty close. And now let's take a look at the first revision of the original math curve based upon those 1.6, 1.8, and 2 volts. As you can see here, it made a very big difference in the top end of the curve. This is probably due to the selection points being too close together. It definitely pays and gives you a much more accurate curve to space these points out. Seeing a 37% change at the top of the curve definitely tells me I need to go back and select my points to be a little further apart and then rerun the data. And now let's take a look graphically at the MAF curves. In this case, of course, you're seeing the additional lines due to data I just keyed in for demonstration purposes in the other sets. These do not reflect any active math curve I'm using. They're just to show that by making small changes in the data, you can make a big change in the curve. Now here's all those math curves in the 2 volt and lower range. Well, that about covers this one. Hope you found it interesting and useful. If you did, consider subscribing and give me a like if you would. I'm definitely working on several other videos I think you're going to find interesting. So until our paths cross again, y'all take care now, and I'll see you real soon.